picking up where we left off. Lesson 1.7, right? Yep, lesson 1.7. We were ready to talk about definition and justification of vertical asymptotes. So we kind of have a case 1 versus case 2 idea, and just the idea that when you plug in a number value, if you get a non-zero number over a zero number, okay, the idea that at that point, basically your denominator is equaling 0 there, at that point is going to be a vertical asymptote. Okay, that's what we're just trying to bring light to there, that is a vertical asymptote. Because a vertical asymptote, remember, is when your denominator equals 0. So if you're putting a number in, and that makes your denominator 0, there is a vertical asymptote there. Case 2, 0 divided by 0, I know we call that the indeterminate form, but the idea is if you're plugging a number in, and you get 0 on top and 0 on bottom, then at that point, that's something that could cancel if you're getting 0 on top and 0 on bottom. So this is representative of a hole, is that case. What I have location of a hole or point discontinuity. Okay. And then when we talk AP test, you have to be able to justify. You have to be able to use calc language to justify. Okay, you can't just say, it's a vertical asymptote because the denominator equals 0, or, we have to be a little more official. And so when we talk about the limit definition and how we justify a vertical asymptote, we're looking at, looking at the limits. What would be the idea? The limit from the left, if we're talking vertical asymptote, the limit from the left is going to be either what? Up to positive infinity or down to negative infinity, yes? What about the limit from the right? Same thing. It's going to be either up to positive infinity or down to negative infinity. And those are the clues that tell you it is a vertical asymptote. And so, just the idea here that if the limit as x approaches c from the left of f of x equals either positive or negative infinity, so plus or minus infinity, or the limit as x approaches c from the right of f of x equals positive or negative infinity, then we know at x equals c is a vertical asymptote. Okay, so if your if you're approaching value and your limit is either positive or negative infinity from one way or the other, pretty much, we know at that point is going to be representing a vertical asymptote. Okay? Now, example 3. Wait to move the screen here a moment. Example 3, we're going to use this function to find any vertical asymptotes that could exist, and we're going to justify our answer using limits. So, in order to talk vertical asymptotes, what must we do here? We're going to have to start off what? Factoring. So if we go and factor this, hold on a second, I'm checking to see if I have another page. I do have another page 59 here, because that's going to be sorry, okay. Because since I have another page 59, I can zoom this in, not have to try and write so small. Okay, are you guys factoring without me? No? Why not? Come on, guys. Do the math. Factor without me. Start with the denominator if you want. What do you know about x squared plus 3x minus 10? X and x. Multiplying to be negative 10, adding to be 3 is going to be plus 5 minus 2. Okay, numerator. I have confidence. 2x squared is 2x and x, yes? Give this a try with me, okay? I'm hoping I'm starting to instill some confidence that you guys can do a little bit of guess and check here and make the easier type work. So 2x squared is 2x and x. What about 5? That has to be 1 and 5. Now, my options are 5 and 1 or 1 and 5. What's a logical guess here? 1 and 5. And why are you guessing that? Okay. So he says because 2x, when we do our outsides, 2x and 5 will give me 10x. And then 1 times x, 1x. A 10x and a 1x could make 9x, yes? I also looked at the fact this is an x plus 5 right here. So would it make sense that maybe the 5 goes with the x if something cancels? Possibly. I never just assume. I always check. If it multiplies to be negative, I need a positive and negative. I need a positive 9. So we need positive 10x minus 1x. And what does indeed happen? You have a cancellation, don't you? So, now, the question was to find any vertical asymptotes that exist and talk about that. And I will say that this is now equal to 2x minus 1 over x minus 2. Now, if we're going to talk about this in terms of limits, okay, well, first of all, where is there a vertical asymptote? At where?
2.
Okay. At x equals 2, there is a vertical asymptote. And we know it because of our algebra skills there. But if we talk limits, so there's a vertical asymptote because, so we need to think about the limits here. We need to think about the limit as x approaches 2 from the left, not f of x, but h of x. And we need to think about the limit as x approaches 2 from the right of h of x. Now, without grabbing our calculator, I know you hate when I say that. Without grabbing the calculator, how can we find those limits? Can we plug in something close and think about what happens? Okay, so if I'm going to kind of set up a little chart here. If I use, let's see, so 2 from the left. 2 from the left. I'm not even going to, and it's not even about the numbers precisely, is it? It's about signs. Because we know it's a vertical asymptote. We know it's either positive or negative infinity. But which one is it? So, 1.99. I'm going to use my simplified version here, yes. 2 times something under 2 minus 1 is going to result in a positive, yes? Because that's going to be almost 4 minus 1. Okay, that's a positive on top. Something a little less than 2 minus 2 is going to result in a what? A negative. So what do we know about as we approach from the left? This is going to be negative infinity. Sorry, that is a sideways negative infinity sign because I didn't leave room like I should have. Here, let's see. Aha. Well, that doesn't look like a good negative infinity sign either. Man, struggles. Okay. Now, if we go 2 from the right, so say 2.01, 2.1, you know, something from the right. If we plug it in on top, 2 times something a little bit bigger than 2, minus 1, that's positive. So that's like 4 minus 1 again. On bottom, something a little bit bigger than 2 minus 2 is also positive. And positive divided by positive is going to be positive infinity. Okay, so again, that's talking about our vertical asymptotes using limits. Okay, down below, we're going to explore limits at infinity in order to help differentiate between the two conditions. If we recall lessons from pre-calc relating to analyzing the in-behavior functions, the exercise below uses prior knowledge to find each limit at infinity. Okay. This is where I was going to look at these notes a little bit more during lunch and I ran out of time, but if we think about pre-cal type stuff here. Okay. Sorry. An internal aha moment of now I understand. I looked at this and was confused. Okay. If we were to FOIL this out, what would be our highest power? X to the fourth, correct? And if we think about x to the fourth, what do you know about x to the fourth? What can you tell me about x to the fourth graph? I don't care about the rest of it, but just an x to the fourth graph.
It's bounded in some way.
I figure it's bounded in some way.
Is it like a wider parabola?
It could be. Okay. So an x to the fourth graph could be like a wider parabola. Or do you remember the other option? Because there's other terms here, it also could be more of a W-type shape.
That's what I get the word.
I can't even laugh because I did the same exact thing.
My only thing was is as I washed his hands, it looked like he came from down below and ended down below.
Well,
So it looked like an upside down, blah, you know.
When I thought of it, upside down.
Okay. Now, and why is mine right side up?
It's
positive.
Positive.
Because it's positive, yes? And is that true? Is this going to be a positive x to the fourth? Yeah, it's going to be a positive x to the fourth. It's going to look something like that. If you remember the vocab word for this, it is a quartic. Is a fourth degree, right? It's a quartic. So, if we think about the end behavior here, okay, so this is going to be x to the fourth plus or minus some other terms. Think about that graph. It's going up like this, yes? The question is the limit as x approaches positive infinity. What's that answer going to be? Positive infinity? We did, actually, I almost feel like we did something like this almost back in Algebra 2. Maybe not. Maybe not quite Algebra 2. But the idea that if, as you're going to the right, if this is a quartic, it is going to be going up to, where do I want to put my answer? Positive infinity. Okay? And again, I'm looking, you know, we're looking at end behavior. And if you go back as far as Algebra 2, we use the end behavior of, do you remember up and up? It's up and up because it's positive and it's an even power. You know, like that was the reason we knew, you know, so based on the end behavior, it's a positive at the beginning, so it's a positive leading coefficient. But we know that this graph is going to be going to positive infinity. And I guess I did write here, interesting enough, someone mentioned the word bounded, versus bounded versus not bound. But as x approaches infinity, it's going to be unbounded going up, yes? It's bounded below, but it's going to be unbounded going up.
So this is going to a measured graph, basically.
I mean, for this, yes, that's the idea, is that just, using what you know about the graph. And we didn't even multiply it all the way out, right? Are we okay with that? Because I have a bunch of just kind of little notes here, but I think that's the gist of it. What do you know about B?
X to the third is the highest.
Okay, so it's a positive 5x to the third, yes? Which means this is a cubic, if you will. What's the idea of a cubic graph?
Does it start low and end high?
Okay, because it is a positive coefficient out front, it starts low and ends high, right? If it was a negative coefficient out front, it'd be just the opposite. Okay. What do we know here? As x approaches negative infinity, where are we going to be going? We're going to be going down, aren't we? So we're going to be going down to negative infinity. So I have written in a cubic function with a greater than 0 will fall as x approaches negative infinity. F of x decreases without bound. So, and maybe I should be throwing in, the fact that here, f of x, we throw in that vocabulary there, it decreases without bound as x approaches negative infinity. Over here, the function was increasing without bound as f of x approached positive infinity. So, again, a little bit of vocabulary. F of x increases without bound. And that was as x approaches positive infinity. I do definitely feel like I'm teaching some pre-calc today as opposed to calc, so enjoy it while you can, right? This should seem familiar. It's just we didn't necessarily talk about it with the limit sense as much. So now, what about C? We're changing things up a little bit. First of all, we have to note that there is a fraction, yes? This is a rational expression. So as we look at that rational expression, do you remember how what do we have to look at here? We're looking at the highest powers. Yeah. What do we have in the way of powers? Highest power on top is 3x squared. Highest power on bottom is x squared. What do you notice about these powers here? They the same. What was the rule when they're the same? The coefficients, right? So the fact that my coefficient, basically if you think about the x squareds canceling, my coefficients being 3 over 1, or in other words, 3. So in this case, as x approaches positive infinity, we're going to be going along a horizontal asymptote. And that horizontal asymptote is going to be at y equals 3. Okay? Yeah. So horizontal asymptote at x equals 3. And so that horizontal asymptote at x equals 3, not x equals 3. Yeah. Strike that. It's not x equals 3, it is y equals 3. Something equals 3, right? Okay, horizontal asymptote at y equals 3. So the idea is, what are we trying to find? As x approaches positive infinity. So if you have a horizontal asymptote at 3, what's your graph doing as it goes off to positive infinity? It's going to run alongside that 3. So I'm going to say as x approaches infinity, then y will approach 3.
Can you draw like a picture and show that?
I can. Why my iPad's making so much noise, but it is. So the idea here, here's my fun, lovely graph, right? If I have a horizontal asymptote at 3, and actually we'll have pictures, I think, in some of our upcoming examples. But the idea of that, if I have a graph, there's an exponential decay graph for you. So the idea that here's a horizontal asymptote as x approaches infinity. So as we go off to infinitely to the right, then my y values are going to be getting closer and closer to the horizontal asymptote of 3. Is that what you were asking?
Yeah, how do we know it's a horizontal asymptote?
Because when the powers match, when your highest power on top match and your highest power on bottom match, well, your lead powers tell you the horizontal asymptote. Okay, so when it's a fraction, look at the highest power on top, highest power on bottom. When the powers match, use the coefficients. And then we have special rules for if the power is bigger on top or bigger on bottom, and that's what we're getting ready to talk about with the next one. But that was one of our 3 horizontal asymptote rules. If you dig back deep in your brains, right? Does that answer your question for the brief moment until I go to the next one?
Yeah.
And we'll talk about the next rule here, okay? So the next one, as you notice, it's a rational function again, right? It's a fraction is what I'm saying. Biggest power on top, 5x. Biggest power on bottom, x squared. What's the rule here?
It's either 0 or none.
Yeah, 50-50 shot here, yes?
Probably 0.
It is. Okay, and you could also think of this if you reduce an x, it becomes 5 over x. Well, think about what's happening. This is actually as x approaches negative infinity, but whether it be as x approaches negative infinity or positive infinity, you're going 5, so a set number, dividing by an increasingly larger number, whether it be larger in the positive sense or larger in the negative sense. So what happens as my denominator gets bigger and bigger and bigger? So, for instance, let's go with numbers you know. 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. I'm getting smaller and smaller numbers, right? Which are taking me closer and closer to, or smaller and smaller fraction values, which are taking me closer and closer to 0. Okay? So, because that's the idea, if you plug in infinity here, so bigger and bigger numbers, then the rule here is if the power in the denominator is bigger, then you're tending to a horizontal asymptote of y equals 0. Okay? So, and we talk about the denominator power being bigger than our numerator power. That's, the gist of what I'm talking about here. Okay, that is when we look at y equals 0 as a, can I say HA and you know what I mean? Horizontal asymptote. So in this one we can say as x approaches negative infinity, then y approaches 0. Okay? Let me get a couple of pictures on the next page too. So Okay, so left this all on one page. I don't need a lot. There's not a lot of writing here. There are 4 possible outcomes when you explore behavior to the extreme right or left. So as we approach positive infinity or negative infinity, being the extreme right or left. A, the curve can increase without bound. Perfect example here, parabola, the quartic we did earlier, as x approaches infinity. So what's happening here? As x is going farther and farther to the right, where's my graph going? Up to positive infinity, yes? So this is as x approaches infinity. So as we go farther to the right, then y is approaching infinity. And that's going farther and farther up. Okay? A curve can decrease without bound. Okay? So it can increase without bound and go to infinity. It can decrease without bound. So this one, as x approaches negative infinity, so as we go to the left, where is my graph going? And it is going down, yes? So it's going down to negative infinity. Okay? So there's another option. The curve can become asymptotic. That doesn't even sound right, but that's the word I'm trying to say there. Asymptotic? I don't know. Okay, the curve can become asymptotic to the x-axis. Asymptotic. I don't know. Okay, so with that in mind, the x-axis being what y value? Y equals 0, yes? Okay, so if that is the y value, or the y value of 0, that means as what? In this case, as x approaches infinity, as we go farther and farther right, we're going alongside that asymptote, yes? And so we could be going to 0. Or the curve can become asymptotic to a specific y value. So as x approaches negative infinity here, as we go to the left, where's my graph going? It's going where? Alongside the y value of 3. And so thus the specific y value. Okay? So, calculus knowledge for asymptotes. Revisiting the rules for finding potential horizontal asymptotes for rational functions from pre-calculus, you can use the idea of a limit in calculus to see why those rules hold true. So 1, if the degree of a numerator is less than the degree of a denominator, so bottom heavy, then the limit is 0. We talked about that one on the previous page, right? If the degree of the numerator equals the degree of denominator, powers equal, then the limit is the ratio of the coefficients of the highest degree. And so there you see the written out limit. And 3, if the degree of numerator is greater than the degree of the denominator, so top heavy, then the limit does not exist. Or in other words, it depends. Because you have no horizontal asymptote at that point. Okay, so you're probably going either up to positive infinity or down to negative infinity. You might have a slant asymptote, is what you might have. And we will look at those as well. Okay, so moving on. You know what? I was moving these pages around. Wait a minute, now I'm all out of order, aren't I? There were 60, we just did 60. Where'd 60? I had another 61. Where'd it go? Do I not? There it is. Don't mind me. This is what I normally do in the morning. I just didn't get it done today. There we go. 61. I definitely feel like this is going back to pre-calc, because I feel like this is how I originally taught it. Well, maybe I don't teach this till calc. It's confused in my head, I guess. Yeah, now I feel like I taught it in calc last year, not pre-calc. Okay. Anyways, in order to do some of these limits, looking at the calculus view, we can talk about a division method, where dividing every term in the rational expression by the highest power of x that appears in the denominator. Okay, highest power of x that appears in the denominator. Okay, and then we can apply our properties of limits to each piece. Now, you're going to notice this very much goes along with those pre-calc rules we were just talking about with powers. But this is more the calculus term. So, notice we said divide each term, right? Divide each term by highest power in the denominator. That's what we're going to be doing. What is my highest power in the denominator in this case? X squared. So we're going to go through and we're going to divide. There's 5 different terms. All of them are going to get divided by x squared. And we're going to look and see what happens. So the limit as x approaches infinity. I'm going to write out the long way for right now. 2x squared divided by x squared. Minus 10x divided by x squared. Bear with me, okay? All over. X squared divided by x squared. Minus 8x divided by x squared. Plus 15 divided by x squared. Yes, I know it's a lot to write out. You get the hang of this, you can do this in your part in your head. And this is where our shortcuts come into play, okay? Now, clean this up with me, because a lot of it will clean up reasonably well. 2x squared over x squared becomes 2. Minus 10x over x squared reduces to 10 over x, if you will. X squared over x squared reduces to 1. 8x over x squared, 8 over x, and 15 over x squared, 15 over x squared. Now, this is the limit as x approaches infinity. So, as we, quote, plug infinity in, so we're plugging the idea of infinity in. So the limit as x approaches infinity of 2 is what? 2, right? A constant is just always a constant. Minus 10 divided by an increasingly bigger number. What's that going to go towards? What? 0? That was my example of like if I have 1/2, 1/3, 1/4, 1/5, 1/6. My fraction is getting closer and closer to 0. Yes? So that value is 0. My denominator. As we approach infinity on 1, it's still 1. 8 divided by an everly increasing bigger number. Still 0. Yes? Anytime you have a constant on top dividing by a bigger and bigger number on bottom, it's going to be 0. Plus 15 divided by infinity squared, if you will. Still 0. What does this work out to be? 2. Okay, there's the calculus behind it. So our limit as x approaches infinity of f of x equals 2. Does that agree with my graph? As x approaches infinity, yes. What are my y's doing? There you go, running along this, and y is approaching 2. Are we okay with that?
How are we going to know when to do like all of this stuff?
Practice.
I'm just going to recognize.
I mean, it's what it comes down to is, you know, right now we're putting a bunch of tools in your toolbox, and I mean, sometimes there's multiple different things that'll work. Sometimes you just kind of have to process through, you know, what are the options, what, you know, can or can't work. The ones we're talking about today are ones that as x approaches infinity. So if we're talking about as x approaches infinity, can I just put infinity in here? Not really. Because 2 times infinity squared minus, you know, I can't, that's not a value I can just plug in. So as x approaches infinity, we need to look for different options. At least we're talking with fractions here. And so this is, you know, this is a technique when we have x approaching infinity or negative infinity with fractions. Okay, with our rational functions is what I should say. Okay. Oh, let's look at the next one. As x approaches infinity, and by the way, let me come back and look. Does this make sense based on our pre-calc rules? The power's matched, yes. The coefficient is 2 over 1, which is 2. That means there is a horizontal asymptote at 2, yes? And so that means there's some kind of end behavior having to do with 2. Now, on B, what am I going to do on B? What is it we're going to divide by? We're going to divide everything in the numerator and denominator by x squared, because the largest power is x squared. Now, can I skip the writing it out and just go to, well, the first writing it out? Like, what is x divided by x squared become? 1 over x plus, what's 3 divided by x squared? 3 divided by x squared. Denominator, x squared divided by x squared is 1. 4x divided by x squared is 4 over x. Plus 5 divided by x squared is 5 divided by x squared. What happens is we start putting values in here. As you put infinity, every time you put infinity on the bottom of those fractions, each of those fractions is going to what? 0, yes? So we're going to be looking at 0 plus 0 divided by 1 plus 0 plus 0. And so, what do we know? The limit as x approaches infinity of f of x is equal to, what is my limit? 0. So I end up with zeros over ones, or 0 over 1, excuse me. Does that make sense on this picture? There is a horizontal asymptote here at y equals 0. Okay. Oops. Yeah, this is right. I just need to zoom in, don't I? Ooh, really big. Okay. This one, if we use our pre-calc rules, what are you going to say about asymptotes? Bigger power on top, no horizontal asymptote, yes? So let's explore what happens if we're dividing by the biggest power on bottom. What are we dividing by? We are going to divide by x. Okay, so the limit as x approaches infinity. What is x squared divided by x? That's x. That's interesting, isn't it? Because we're not used to having just an x. Minus 4x divided by x. Minus 4. Minus 3 divided by x. 3 over x. X divided by x on bottom is 1. Minus 2 divided by x. 2 divided by x. Okay. Now, with that in mind, what happens when we start plugging values in? As x approaches infinity and you plug it in for x, that is what? Infinity, yes? So if you're at infinity, you take away 4. 3 over x is just going to be 0. So you take away 4, then you're going to divide by 1 minus 0. What are we looking at there? A really big number, taking away 4, dividing by 1. This limit is going to equal infinity. The limit as x approaches infinity of f of x is going to equal infinity here. Does that make sense looking at my picture? It does, because as my graph is going off to the right, where is my y value going? It's going up. It's going along that slant asymptote. Okay. I know we did this last year. I think we did this last year. You can actually find that asymptote. Do I dare throw this in at you? Remember anything about your synthetic division? Because in order to find the slant asymptote, you divide. So we're going to take x squared minus 4x minus 3 and divide by x minus 2. So for x minus 2, I'm going to put a 2 in my box. My coefficients are 1, -4, and -3. She hates it that much, she's throwing her calculator. Yikes. Okay. Drop the 1, multiply. 2 times 1 is 2. Goes under the -4. Add -4 and 2 and get -2. Multiply. 2 times -2 is -4. Add -3 and -4 and get -7. And so now, remember this guy here is our remainder, but this 1 minus 2 is 1x minus 2. So we have a slant asymptote at y equals 1x minus 2. Well, plus -7 over x minus 2. But notice, -2, rise 1, run 1, rise 1, run 1. That matches up, doesn't it? So that is our slant asymptote of y equals x minus 2. Okay, I got one more page. Where are we at on? Okay. We summarized and discussed here. So based on observations of 6, the limit as x approaches positive infinity or negative infinity. As we looked at those limits as x approaches positive infinity or negative infinity, they were always equal to, well, the first two, a and b, which had the horizontal asymptotes, they were equal to the horizontal asymptote, yes? And so if we look here, this is why I do this all ahead, so I quit making that silly mistake. B, as in, if we talk about the fact that y equals b is a, I'm going to say HA, a horizontal asymptote of the graph. Okay. Functions with slant asymptotes. If you go back to the bottom example there, yes? As x is approaching either positive infinity or negative infinity, where's my graph going to be going? It's either going to be going up to positive infinity or down to negative infinity, depending on which way your slant asymptote goes, right? And so the idea here that these are going to go to either positive or negative infinity. Options include here, you can use long or synthetic division to find your slant asymptote. You can also test values. Use long or synthetic division to find slant asymptote, and testing values also works too. That is, I'll say test values to find end behavior. Earlier on, we looked, I know it was in today's earlier somewhere, limit definition, justification of a vertical asymptote. We did it earlier. Now if we talk about limit definition of a horizontal asymptote, if the limit as x approaches infinity equals b, or the limit as x approaches negative infinity equals b, then y equals b is a horizontal asymptote of that function. And that's what I'm going to write here. So if the limit as x approaches infinity of f of x equals b as in a number, or the limit as x approaches negative infinity of a function equals b as in a number, then we can know that y equals b is a horizontal asymptote of f of x. Okay. One last thing at the bottom. As we look at the bottom here, yes, they give a graph, but if we're talking algebraic techniques here to find these two limits, the limit as x approaches positive or negative infinity of this function. Okay, well, rational functions, we were dividing by the largest power, yes? Largest power in the denominator. What's the largest power in the denominator? Is it kind of equivalent to x? Because there's an x squared, but that x squared is under a radical. What's the square root of x squared? X. Now, what's going to have to be true about that x when it comes out of the square root? It's going to have to be positive. And so what they suggest doing here is dividing by the absolute value of x. Because as we're putting in positive versus negative values, that will matter. And so if I look at the limit as x approaches, I'm going to do positive infinity first because my brain works better with positives, of 3x minus 3 over the square root of x squared plus 4. Well, if we divide everybody by absolute value of x here, what's going to matter? On top, what's 3x divided by absolute value of x going to kind of represent? Let's see, wait, how do I want to do this? Yeah. I don't feel, if you take 3x and you divide by absolute value of x, okay, you said 3, yes? Okay, 3, sorry, I was processing. Minus 3 over absolute value of x, which that's going to be like 3 over x, right? On bottom, mean, if I write this all out, I could write the equivalent of, when you do the square root of x squared, you're dividing by this idea of absolute value of x, it's just going to become a 1. This one over here, I'm going to put it as the 4 divided by x squared, because under the radical, that absolute value of x is still an x squared, right? But what we need to look at here, as we put in increasingly bigger values, right? 3 is 3. 3 over an x is going to be nothing. On bottom, when we do the square root there, it's going to be the square root of, well, 1 is still going to be 1. 4 divided by a big number is 0. What do we end up with here? 3 over 1, yes? And so that's the idea that up here, it's approaching 3. We'd have to think slightly different on the negative infinity, because you have to think about plugging in negative values, and so that just changes it to a negative 3 outcome. Okay? So, we got almost everything done. Almost. Lesson 1-7 homework. Look at it for Monday. Wait, do more than look at it for Monday. Do it.
Have a good weekend, Mrs. Social.
Thank you. You too. Good luck on physics, guys. Sorry, no free time at the end. I know. Would have been nice, but it wasn't in the cards for today.